spilt it.
Great. Hello, everyone. So, this
Hi.
is my girlfriend Megan. You may have seen her on the stream before. We are actually going to be continuing the series of Jono Explains Things to Megan. I don't think there's anything to clean that up, so we're just going to have to live with it. Megan wanted to continue the tradition of eating on stream, so she has her snack of choice, Pocky, and a
It
cup
had
of
no
coffee.
strawberry.
Oh, yeah?
I spilt the coffee when I was dinging it like a
Well,
triangle.
don't get it on JJ Watt, right?
They couldn't even see that.
Yeah. Oh, you gonna get
It's a car
up
that
close
he
and
made
personal? Yeah.
out of a pizza box, and it hung on our Christmas tree.
Yeah.
This is the one thing he asked to be on it. So.
All right. So today we are going to be talking about the topic of thermodynamics. Now, this is a topic that not many people understand, and I wouldn't necessarily say I am a professional on, even though I am going to school for engineering. Um, I had a professor explain to me that make the claim that the first time you try to learn thermodynamics, you don't understand it. And then the second time you try to learn thermodynamics, you think you understand it. And then the third time you accept that you don't understand it, and then you start using it practically. So we are going to be trying to explain in terms that people that aren't necessarily from an engineering background can understand. So that's why I wanted to get you on, so that you could make sure that I'm staying true to that demographic, and so you can ask questions when you feel I'm not explaining things thoroughly.
Right.
So,
if anyone doesn't know my background, dance, didn't do well. That's like, I can't talk. I could not talk at all today. I did not do that well at high school either.
Well,
So,
you did
okay.
fine. You were just a little unmotivated, I guess.
Yeah, I didn't really like it.
Yeah.
Does thermodynamics have to do with like temperatures?
We'll get to the whole thing. So.
Okay, that's what it sounds
Yeah,
like.
yeah. Okay,
like the whole
so
concept of turning something.
we can start out by breaking down the word, I guess, since we're already there. So we will
You're
write
welcome.
down thermodynamics.
Sorry, this stuff.
So this is a two-part word, thermo and dynamics.
I think mix is its own part. So I think it's dyna and then mix.
Well, yeah, but dynamics itself is a word. And so if we add thermo on top of it.
Okay.
So what we're doing is, so thermo obviously is dealing with, like you said, temperature, more specifically dealing with heat. So heat is a form of energy. And so it actually, in a sense, is all energy. So when we have movement, when we have anything, it's all kind of boiling back down to the baseline energy. So when we have temperature, well, actually,
Well, that's what I'm saying. That's what I was about to say. Is that why like cold isn't part of it? Because the particles, when something is cold, or the atoms don't like vibrate as much.
Well, we can't measure something as being a certain amount of cold, because what we're dealing with
we just deal
is
with the lack of heat.
So when we have something that's cold, it has less heat than we are used to, and that's why we feel it is cold. So thermo means it's dealing with heat and energy. Dynamics means that we are talking about possibly talking about changes in these states of energy and heat.
So cold isn't out of the question for thermodynamics. It's just generally not touched upon.
No. So the word cold is just in thermodynamics is defined as less heat.
Right.
So,
okay, but like
yeah.
essentially.
Yeah.
Our word for it doesn't matter.
Yeah.
Concept.
The one thing to keep in mind is that thermodynamics isn't necessarily restricted to temperature. Just because it's talking about heat isn't necessarily temperature in a sense, because there's a lot of things that
like
heat.
Friction.
Yeah. So there's a lot of things that happen with heat and energy that don't necessarily deal specifically with temperature. So we might get into those contingencies, but I'm thinking that today we're going to try and keep things relatively broad and the summarization of thermodynamics. And then if we want to get into the specifics later, we might save that for another day. So this is what thermodynamics is, and I'm going to clear the board here, and we're just going to start talking a little bit about the basics. So, with thermodynamics, one of the key things is defining a system. So, what we have to figure out is what are the boundaries of what we're talking about. And so, if we have a environment, say we have this room that we're in,
like a physical boundary, like a fence, or like boundaries that you set
we're
yourself?
just sort of imagining where the boundaries are, because we
Okay.
can only really analyze things from within the boundaries, because if we're outside the boundary, then it's an infinite boundary. Does that make sense?
Gotcha.
Yeah.
So we set the boundary.
Yeah, so we want to define where we are. So let's say that we have the room that we are currently in. Here is me, and here is Megan.
Why'd you give me a fat head?
It's like the same diameter.
I don't know. My neck's
Let's
jammed up in
okay.
there.
Are we gonna actually measure this? Let's go. That's pretty close. It's a little bigger.
But you didn't
But
give me any
if we rotate it by 90 degrees, it's like you took my head and rotated it. So I think we're good. But all right. So we have this environment of the room that we are currently in. Now there are a couple different situations where we could describe a boundary, and so what we have to define is what is in the system and what is in the environment. And in thermodynamics, sometimes there is a third one here, to where because we're in this specific room, there may be some conditions that aren't necessarily true outside of the room. But we'll keep it simple for this case. So we can just go ahead and draw a box around whatever we want. We can even draw, it doesn't have to be a box, we could draw whatever shape we want.
Can we get
So
a trapezoid around my foot?
we could. So if we wanted to draw a trapezoid around Megan's foot, we could say that this is our system. And we can start doing analysis based off of heat entering and leaving the system, what's happening. Obviously, her body is creating heat through the normal processes that bodies do so, and that would be providing heat to the system. But there also might be some drafts coming in, bringing heat and whatnot. So, but the key to get here is that we are not restricted in what we define as our boundary. So we could put one around me. We could put one around both of us, or we could just go ahead and put one around the entire environment, and all of these would be considered valid boundaries. But the definition of what's going on inside them can change. So that's just sort of a baseline for what I mean when I'm talking about the system. The system is whatever's within this boundary we're defining. So for some vocab, we could say that this could be an open system, which currently it is. An open system means that mass and energy can cross the boundary. So if we imagine that that door is open, Lola could enter the room, and mass would be entering the system also. And then air can also get through the cracks under the doors. So
Air is important.
yeah.
Air is important.
So in most cases, we are going to have an open system. In fact, in all cases that are not ideal, we have an open system. But we have.
Yeah, I mean, technically, this is open because the crack under the door.
Yep.
Like, unless it's vacuum sealed, it's basically an open system.
Even on a completely like microscopic scale, there is still some mass transfer through the walls. It is just extremely slow. So.
Well, like, okay, but if you think about like pressurization in a spaceship.
Yeah.
It's pretty much like not vacuum sealed because you're not sucking the air out of the capsule, but like it's basically it's a vacuum seal.
Yeah. So the air is trapped inside.
A tiny bits of particles that aren't obviously because nothing ever actually touches. It's like really, 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 really close, but nothing ever actually touches, right? So then, why does like if space is nothingness and like you see in movies and stuff that airlock opens and everything gets sucked out, like why doesn't it treat it like a crack in the glass, and when you tap on the crack it gets bigger? Like why doesn't it take that little bit of air and slowly go
Well, we might have to save that one for another day. I feel like that's an explanation in its own. But essentially, because of the way things are bonded, they have a certain strength they have a certain resistance to being pulled apart. So if there were enough pressure within the vessel, then you would have a problem. But because it is engineered in order to keep that air within, then we don't have too much of a problem. And so what the case is, if we have an environment like a spaceship, which is vacuum sealed, in most cases we can imagine that system is a closed system. And what a closed system is, and we can draw that with a just like a solid line. A closed system means that energy can get in and out. So this is heat.
That doesn't seem like it's closed.
But if we try to put mass into the system, it cannot enter through the boundary. So that's what I mean by a closed system, is that
kind of like a cell membrane.
In a sense, so cell membranes are selective in what they allow to cross over the boundary.
Right, which is kind of what this is. Like mass can't get in, but other stuff.
But so we can have heat enter the system, and we can see that, like, if you have a spaceship out in orbit or in space, if the sun is within view, you are getting radiation from the sun, and that's heating up the vessel. Now, this isn't the same as
radiation or the actual heat of the sun.
Well, the radiation is from the sun, and radiation is a form of heat transfer.
But radiation isn't actually hot.
It is when it hits you.
But like X-rays and stuff aren't those? That's why they put like those things. Packs over your belly so you don't scrape your organs.
If you had enough of an intense beam of X-ray, it would heat you up. Well, okay, no. There's difference between frequency and amplitude. So gamma rays and X-rays have different frequency, but amplitude is how powerful they are.
Right.
So it's reasons why, like, the microwaves can heat up stuff inside them, but they're not necessarily a deadly frequency because they can't break through the barrier that they put on the microwave. But okay, so a closed system
I used to try radiating myself.
Oh yeah.
I tried putting my face against the microwave to see if I could get more brain power. I was weird. I was like 6 or 7 at this time. Please continue.
So, open system means that mass and heat can both transfer over the border. Closed system means that only heat can transfer over the border. And we have a third system, which is the highly idealized case, which is a isolated boundary condition. And this basically means that heat cannot transfer over the border, and neither can mass. So whatever's in here is going to stay in here, and whatever's out here is going to stay out here, and they will not interact.
It's a beautiful
topic. Yeah. So the problem with these systems is that if we actually had a isolated system, we wouldn't know what was going on in there because we can't take any measurements, because any tampering with the system would cause it to not be isolated. Does that make sense?
Couldn't you, like, before you sealed it up, whatever, couldn't you put stuff in there that would measure it for you during the experiment?
Yes,
or
but
would that mess up the experiment?
It's a weird situation. So yes, I guess that would technically make sense if you had something like a measuring device that was running while inside. But the problem is that we can't necessarily. It's hard to transfer information across an isolated system. So you would technically have to break the isolated system to open that. But that is true that if you had the measuring device within the system, you could technically, like, record the measurements and then look at them later.
Like on a computer.
But if you're asking for real-time measurements, this is not a case that you necessarily want to work with, because in real practice you can't necessarily have a thermometer sticking in there, because then that's a break in the seal. So but these are the three cases.
So it has to just be an empty room with a vacuum seal? That doesn't seem like it.
No. So an isolated system can have stuff in it, but we can't tell what's happening within because we're not getting any information out.
Right, but you're saying that putting in a thermometer would mess it up, and it wouldn't be.
If we had a thermometer sticking across the boundary, so that we could.
Saying, like, if we had, like, I don't know if there's anything like this, but probably like a thermometer in there, and it had some kind of like Bluetooth thing that could send the information.
That's the problem.
To your computer.
If Bluetooth was able to cross the boundary, then so can heat. Because if any waves can get across the boundary, then it's no longer an isolated system. That's why it's an ideal case, and sometimes we can.
So basically, it just has to be a completely solid room with nothing in it.
Well, it can have stuff. It can have stuff in it,
nothing that we could use to our advantage. So there's no point in having stuff in it.
But the theory of it is important because there are situations where we can simulate a environment that may be a closed system as an isolated system, and the math is easier. Does that make sense?
So the closest that we can get is an isolated system.
Oh no! So we can't have an isolated system, but we can have if we had a closed system, but there was very minimal heat transfer, then we could claim that it was an isolated system for math purposes. The math wouldn't be exact, but we'd get really close.
Basically as close as we can get. Like why people generally will like test on rats if they're looking at lifespan stuff, because they're very similar to us and they don't have to wait 80 plus years to find the results.
Yep, that's a good analogy.
Okay.
So we have our three cases of an open system, a closed system, and an isolated system. Technically, every system that we will ever see in practice is an open system.
I was gonna just make a really weird noise and I couldn't do it.
Oh,
Continue. Closed system.
So every situation is an open system.
Open system.
But in practical purposes, there are systems that we can consider closed because the mass transfer is so slow.
Okay, wait. So, sorry. Open system is like this room with the door open.
Yes.
Closed system is like basically an airlock.
Yes, it's an airlock, but like say that it's like a metal airlock and we have a heater under it. The heat can still get in there because it can heat things up through the boundary. Does that make sense?
Okay, so closed, right, is the cell membrane, basically, like it.
It takes in the nutrients if we're considering energy as one thing and mass as another thing, it can take in energy through the membrane, but it can't bring mass in.
Right, because cells generally won't let in like viruses like that.
They try, but it doesn't.
Well, I know, but like you know what I'm saying. Like they won't let in a physical object. It's generally the nutrients that they just need. Anyway,
okay.
So then
an isolated system
is like I have this hollow concrete cube.
Mm-hmm.
There's no opening to it. There's no vacuum seal. It's physically just a concrete hollow cube.
Mm-hmm.
That's isolated.
Yeah. So the isolated system, you can imagine, going back to the last segment of this series, I talked about Schrodinger's cat. So the isolated system is the box we put Schrodinger's cat in. We have no idea what's going on inside.
How do we...
And we don't know until we open it up.
Quick question, though. How did we put the cat inside if it's isolated? Because then it would only be closed.
We don't make it isolated until we put it inside.
So we have a box without a lid, and then we
put the lid over top of it.
Slab over the top.
If you want to encase a cat in concrete, yeah.
Which I don't. I'm not for that, guys. You're over here. I'm not for that, okay? Whoever's the one person watching, thank you, even if we're just like...
It may be me. Sometimes it thinks that I'm a person watching, but I'm not sure why. Yeah, so we've gone over some vocab. We've talked about heat. We've talked about mass. We've talked about the 3 boundary conditions. And now I figure I'll give a little rundown on some of the laws of thermodynamics. And so these are the laws that everything has to follow because everything in the world boils back down to thermodynamics in a sense. Unless you want to talk about mathematics, and then everything boils down to mathematics. But if we're talking about thermodynamics, then psychology is a version of biology, and biology is a version of chemistry, and chemistry is a version of thermodynamics. So it's kind of those things. Biology. Yeah. So
I'm decent at
if we are talking about the first law of thermodynamics, have you ever heard of the first law of thermodynamics?
We don't talk about thermodynamics.
That's very close. Apparently, I'm eating this now.
I've been meaning to feed you the past few, and they were in
my
mouth instead.
Interesting how the mass cannot transfer across the boundary.
I'm not that bad.
I'm pretty bad. I make bad jokes.
He makes really bad jokes.
So the first law of thermodynamics deals with energy. You've probably heard the sentence that people usually use to describe the first law of thermodynamics. It's not complete,
I think you told
but
me. I just don't remember.
The first law of thermodynamics is energy conservation. So it means that energy cannot be created or destroyed. So in a sense, it's always turned into something else, which I guess you could say was recycling.
Recycling energy.
So there is an equation that is used for this. We say that our energy is equal to our heat. So this is the change in energy is equal to the heat and the work minus the work. So this is the heat in minus the work in. So if we imagine we have our system here, this is our magic box.
In?
Yeah, in.
Like, why is heat a Q?
That's just what we usually use for heat. So
what
that's.
Does H stand for then?
H is actually enthalpy, which is dealing with.
Why not E? Oh, because E is energy.
E is energy. U is internal energy. There's a lot of things, but for now, let's just remember that Q is heat, W is work.
Does that mean that's what goes into like pushing an object? Let's say.
Yeah.
Like,
So let's say
exerted.
Let's say that
from a specific.
I was going to delete
being.
that. So let's say that we have our system here, and this system is a piston in a chamber. So this is our chamber, and we have our piston here.
Piston is like the thing in the car, like in the engine that was.
So we have our chamber here. We have some gas in here.
It looks like, you know what it looks like to me? And it's all like, there's only one thing left to do. Push the red button.
Yeah, like. I can see that.
It looks like, or an ice cream cone.
So we have our piston.
Like, I just ignore me.
And this is our system. So we're going to draw this boundary line like this. And we can include the piston. A lot of cases in thermodynamics, especially when you're just learning in like a first class, we will assume that the piston doesn't have any mass. Now, obviously, this can't actually happen, but for math purposes, it makes things a lot easier.
Okay.
So what we're doing is we have this gas. This gas is at a certain temperature, pressure, all the things you need to know about a gas for any reason. And basically, to explain this equation, which may be somewhat intuitive, if we have a certain amount of energy in here to start, right? So we have this energy E in here. I could probably draw that a little darker.
You like constellated it, so I couldn't really see. It's like, oh, do you see the man shooting an arrow at the wild boar, and the boar is trying to feed its children? And you're like, no.
I never really saw them either, but
there's a couple I know, but
so we can imagine that we have this. We can have heat transfer in, so that's what our Q in is. If the heat were going out, this would just be a negative number. So we call it Q in just for purposes of writing this equation, so that we don't have to switch around things. But you can remember that in is positive and out is negative. And then
so if I said W out, I'd be adding the work.
Correct. And I'll explain in a second how this makes sense. So we have our Q in, and this piston can be moved. So if we push the piston into the cylinder, then we're compressing this gas, correct?
Right, because it'd be more pressure within the boundary.
Yes. So if we compress this gas, then it has an ability to do work and push this piston back. Does that make sense?
Yeah, so, it's like when you eat a bunch of beans and you get all gassy, but then it's all and it hurts.
I may have actually written the equation backwards.
Then you fart or you poop.
So I'm actually going to erase this. So because I'm saying that this is the change in the energy in the system,
did my gas analogy
I did this
make
backwards.
you find something?
I think so.
Did me talking about farts help you with the engineering
Let's go with yes, just so the people back home have something to root for. So I'm going
Always root for farts, guys.
I'm going
They're
to
funny.
switch this to Q out and work out. Sorry about that. So we're saying that
I work out. Don't look at my back.
actually, I gotta make sure I get this right so that people aren't screaming at me.
Look it up.
Well, okay.
I mean, I guess that's what we're
It makes sense, but so basically, we want the positive thing to be what is when we put a positive number in here, it makes sense, right? So
yeah.
If so, we can have work in. If work is in, then that's a negative number because this is what we're saying is positive, is work out. So if it's a negative number, then we're adding it. The system is gaining energy. Does that make sense?
When we put the piston into the
cylinder. So when we push the piston in,
it's gaining energy.
The system's gaining energy. So work in is negative in this equation because we have this minus here.
Never mind. I was thinking, wouldn't the piston be losing energy because that's the thing that initiates movement, but we're technically the one who's initiating the movement.
So we're kind of losing energy into the system, but the system has the potential to push back. So the system is gaining energy.
It's
and
like
also,
momentum. Like it gets the energy from us and then pushes it back.
Yeah, in a sense. So we have our Q in. That is also, if the Q in is positive, then the system is gaining energy because if we shoot X-rays into here and heat up the system, then we are gaining energy. That makes sense, correct?
We're shooting what into the system to gain
Just
energy?
some sort of beam, I don't know, lasers.
Gotcha.
We could
radioactive
heat up this system. So heat is transferring across the border, and it is gaining a total energy of E. So this delta symbol is for change. So that just means this is the change in energy. All right.
Okay.
So the change in energy is equal to.
Did I ever learn that in like statistics or calculus?
I feel like you've probably. Oh.
Or from you.
I was gonna say, did you take calculus or did?
Yeah, I remember I took it with you. I technically took AP Calc.
Mm-hmm.
Or did we take Stat last year?
We took Stat.
But I definitely took AP Calc before that.
Mm-hmm.
And I was like, yeah, I'll be okay with AP Calc because my school looks really good. And then I'm good at math. I just need a little bit longer than everybody else. Like I just can't do 1.5 lessons every day in a 40-minute period. Like I need
practice. Just for context, if there were a laptop with math homework on it and a laptop next to it that had just a squirrel dancing, I don't think the math would happen. But
no, it wouldn't. But like you remember when I started doing the college algebra stuff, I thought college algebra was the first class you're supposed to take and not college mathematics. And it was like 3 steps into the STEM program, which is so not what I'm going for.
Mm-hmm.
And I needed him on FaceTime and my textbook and my notes and the problem. And it took me like 4 hours to complete a 12-question homework, but I aced the class. I was like the only person that like got A's on the test because I worked hard and I was good at it.
Yep. She's a hard worker and she wants to learn, but sometimes the schooling environment is not favorable
to me. No.
Yeah.
If you can't tell, I get distracted easily.
So, speaking of distraction, let's get back to the thermodynamics. So, this is our law. I'm terrible at drawing a straight line, apparently. It's still not straight.
Isn't there a tool?
There is, but that's cheating.
No. Look, there's even shape ones. Like, you could have just made our heads the same size.
Yeah, I could have, but, you know, when in Rome.
We don't have money to go to Rome.
So this is essentially the first law of thermodynamics. So
that took a while.
It is the conservation of energy. It's telling you that energy is changing if you're adding stuff to the system. It's pretty logical. So if you add energy to the system, the energy in the system goes up. And also, you can't necessarily lose energy because that energy is still there and it could push back.
I mean, you fix my green lollipop.
Oh, yeah?
Yeah.
What, do you think there's, like, holes in it and whatnot? Or did you just...
No, because when we first made it, we were talking about making it rainbow like the
yes,
and then
yes.
that never happened.
We never made the rainbow lollipop. Okay. So we are going to move on and talk a little bit about the second law of thermodynamics. Now, this law could definitely take an entire video of its own, so
I will shut up.
I'm not going to go into that is not how you spell thermo. I'm not going to go into too much depth with the second law, but we will bring it up. The reason that I'm saying this is that instead of energy, we are now talking about entropy. So have you heard anything about entropy, just off the top of your head?
I know it has to do with energy, and that's not just because of that's what the topic we're talking about is. I know it has to do with it. I can't remember if it's like specifically taking energy in or how it changes energy.
Okay, well, I just wanted to see.
I started thinking about like empathy. Like that's what I kind of start thinking about when I hear entropy.
And don't get empathy.
That's not the same thing.
Don't get empathy confused with enthalpy, but so we have entropy, and entropy is a lot of people call it the measure of chaos. I had a thermodynamics teacher actually call this the measure of how many options you have, which is a slightly more positive way of looking at it. But in a sense, entropy is what people usually say is the measure of chaos. So you have to know.
1 to 10, I'd be like a 9.
There are no units in there. I have no idea what you're talking about.
Oh. What was the one unit we came up with earlier? The unit. It's not leprechauns. I don't know why I'm thinking leprechauns.
I'm not sure. Yeah, I don't know. I know you were talking about saying Samato for random code words, but
yeah.
Okay. So entropy. The one thing you need to know about entropy is that entropy, which we usually denote as an S, always goes up or stays the same. It cannot go down. So it is greater than and equal to 0. No, we don't usually talk about speed in general. It's usually V for velocities because velocity also implies direction. But entropy always increases or stays the same in an ideal case. So the reason for this, this is just the law of the universe. So what's happening is all things move towards higher entropy. And a way to explain this is if we had a box here and we put, just imagine chaos? This is like a ball pit, okay?
Entropy is chaos.
Yeah. So we have like a ball pit, right?
How many colors?
How many colors do you want? 6. Okay, so we're gonna.
You're gonna have to do them all. We'll do 3. We'll do
3 colors.
Hot pink and blue.
I have this pink. Is that fine?
I guess.
So we're gonna go pink, and then we'll get blue.
You get the solid ball tool. You can just click into.
And then yellow. Is that what you said?
Yeah. Well, you can't really see that. That's fine. Just leave it.
And then we can copy that puppy.
This is so much work. Why not just grab the solid circle tool?
Paste. All right, but
and just click and drag a whole bunch across that.
I'm just gonna keep drawing a bunch of these while I'm talking. So, all of these balls are on this side of this boundary that we've set up. So just imagine there's a big plastic wall in the ball pit, and
I'm not even gonna go where I was about to go.
Okay, yeah, funny. So we have this ball pit, and there's a wall. It's just a big plastic divider, and all of the balls in the ball pit are on this side of the wall. All right, so that's the scenario we have.
That's America.
So that's.
I'm sorry. I'm sorry. I'm sorry.
We're gonna get through this, Megan.
I'm so tired, and that was awful. I'm sorry.
All right. So this is state 1, right? If I pull this line, if I take the divider out, what's going to happen? Work with me.
They're gonna roll over into the other side.
Okay, so these this organized structure of having all of the do I need to say contents of the pit?
Just say the balls.
Okay, all of the balls are on this side. When you take the divider out, they move to this side. And the reason for this is because over here they're organized. They're all organized to one side, and the universe wants to move towards more chaotic systems. So the balls over here want to spread out. Now this obviously in a real scenario, I'll eat this in a second. In a real scenario, there would be a lot to do with gravity pulling the.
On top first, wouldn't it?
Yeah. So it would want to spread out, but
would the weight of the top one push out the bottom ones?
It would. It'd sort of be like a buoyancy kind of thing. But if we imagine that these are molecules in a box and we have them all pushed to one side, there's a vacuum on the other side. It wants to get.
It's the airlock.
So it wants, when we take the airlock out, it gets sucked into the other chamber. And so this is a representation of how entropy is the driving force in a reaction. So entropy has to go up. So if we see that there is a state that can be achieved by increasing the entropy, by making it chaotic, then the universe will naturally approach that state.
So like if I had a glass of water and I poured it into another glass, that would be increasing the entropy until it settles back into the new glass?
A little bit. So there's a lot going on there, but
but the idea of like it's moving, like it gets craziness and then it settles again.
Yeah. So because I don't know that it's the best analogy, because having it settle back down would mean that it kind of went back to the same state. But
this would too. The balls would all until like some kid.
Our beginning state is all to one side, and our end state is spread out. Does that make sense?
Gotcha.
So
pouring water onto a counter.
Yeah, in a sense. So we have it organized in a glass, and then we pour it all over the floor. And you have to think about that will happen on its own. So let's say that it's teetering on the edge, the glass falls over, shatters, spills the water everywhere. The amount of energy that we need to use to put that glass back together and put the water back in the glass is significantly larger than the energy that we need to just tap the glass and push it over. Or
like smiling and frowning.
We also, in that case, we kind of gain some energy because there was potential energy because it was on the top of the counter and it fell over, but we would have to use that energy to put it back on the counter. But the actual organization itself, there is some irreversibility with that. So that's kind of like the broken glass. So that was an interesting face. Yeah.
Sorry. Looked over. I was like, "Wow." I used to make that face when I was like 7. My parents like, "No, you're gonna eat your vegetables." And I was like,
okay. We're gonna have a pink piston.
Asleep at the table.
Hopefully, there's no jokes to be made about this. So we have our piston here, right? And we are going to.
It's sideways?
It can be a sideways piston.
What is it in? Is it in a box?
It's the same situation we had before. I just rotated it. I believe you. Okay. So basically what the second law of thermodynamics says is if we have a pin, say this is a pressurized chamber, right? So there's a lot going on in here, right? And we have a little pin here holding the piston in place, okay? If we remove this pin and let this expand to where it wants to be, so that it's at equilibrium with the environment.
It's a doorstop.
Yeah. So if we open this this pin and let the piston move outwards, then we can get some work out of that. So it will push out. It will get some mechanical work because it's actually moving. But if we want to push this back, say we want to put the exact same amount of energy in.
Sorry, I was thinking of an analogy in my head, and that was a very painful thought.
Okay. Do you want to share with the class, or is it a little off the beaten path?
I was just gonna say lady problem.
Okay. So if we have a piston and it pushes out, then we're gonna get some work out, right? Right. So we were talking about that earlier. So if there's energy in the system from it being pressurized, then when it releases that energy, it turns it into work by pushing the piston, right? If we take that work and put it back into the system to push the piston back, because entropy always increases or stays the same, if this is a case where we have friction or different irreversibilities, then if we just put the same amount of work in, then we won't get back to where we can lock it with the pin.
We have to put an excessive amount.
We have to put extra energy in because we've lost some energy due to irreversibilities, which is what entropy is essentially saying, is that entropy will always increase in practical situations because there is friction, there's wind resistance, there's everything.
Right.
So,
quick question. You have two doors.
Mm-hmm.
One person just left this one, and it starts to close. A lot of people take that swinging door and pull it back open, walk through that side. Wouldn't it require less energy to take the unmoving door and open it?
It depends.
Since this is going the opposite direction?
Because with friction, all right, there is less friction when things are moving. So it takes more force to get something moving than it does to keep it moving.
Right,
but because it's moving backwards, there's some weird stuff. But yes, in a sense, it would take more initial force because it was moving towards you. But I don't know. I think they designed doors so that it's not that case. But I don't know, because it's slowing down with the brake on the door. But I don't know. I'm not a door expert.
I don't know. I always think about that when I'm going through doors.
Mm-hmm.
There's always a lot of people who open the ones that are closing. I'm like, heh.
Yeah.
Especially when they're like tinted, you can't see through them.
I think the reason that I do it is because I don't have to open it as much because it's already slightly open.
Yeah, and that's another thing.
So I can get through before.
Like use that amount of energy for as long.
Yeah.
Because do you need another one?
Yeah. Okay. Where would I put it?
I don't know.
Okay. So I think we've done enough of a summary of the second law. So we're just going to summarize in general what we've talked about today. And if you want us to go into more depth...
More laws?
No, there are more. There's a third law. There's a zeroth law. But zeroth law. But they're not that important for everyday use.
Why not zeroist? Zero-end.
But it's first, second, third, like fifth, zeroth. I don't know.
I don't get why it has to
So,
do that.
what I was saying is, if you want us to go into depth on any of these specific topics or continue and possibly talk about the zeroth law, then let us know in the chat. And I'm sure Megan will be very excited to continue this conversation.
I have a midterm.
No, I don't mean today. I mean on another day. Yeah.
I'm just thinking about
So we talked about thermo. We talked about open systems, closed systems. That's okay.
Chlorine systems.
Isolated system. So, do you want to give a quick rundown of what those guys were while I write the rest of this?
Open is like you're in a room with an open door. There's a very clear path to the outside, which a lot of, computer people don't find anymore.
Mm-hmm.
Love you.
Oh, yeah? Do you see this adventure race shirt that I got today? Uh-huh, yeah.
Closed could be anywhere from you close the door in that room and it's easy to open to like an airlock on a spaceship because it's sealed. It's pretty much sealed for all intents and purposes, but there's just a tiny little bit that's getting through there. And then isolated is like a hollow concrete cube, and there's no outs or windows or any kind of cracks or crevices. It's just
and
those. No, never mind. I was gonna say the storage bags that you suck the air out of, but they technically have a door.
And so to remind you, this is a completely ideal case, so we can't really reach that. Well, it's ideal because it's perfect in a sense.
Right,
but we can't really get there.
Can't measure anything because of it.
And practically, it's not necessarily what we want because what's inside is immeasurable from the outside. Closed system is still ideal, but because there is still technically some mass transfer at a very slow rate through things like molecules moving out of the way and things moving, but it still allows energy in, and open is complete transfer. So you could say that this is an open boundary because you can say that this cube of air in front of me is an open system. So that is...
This cube right here.
Yes.
My cube.
I'm proud of you.
My companion cube.
And so then the first law is energy conservation. So that is our delta E is equal to Q minus W.
Created or destroyed, right?
Yep. So energy can't be created or destroyed. It can only be changed into other forms.
The first rule of thermodynamics is that we don't talk about thermodynamics.
In most cases, but I felt today it was necessary. And the second law is, if you want to be in technical terms, it is S is equal to Q or T dt and something like that. But
it looks like a
basically
that's been split in half.
Oh yeah, that does that. It looks like you cut his neck off right there, and that's the sword blade.
You cut right underneath his arms, and then you flipped his leg upside down. He was in the middle of doing
Oh, I can see that.
like
yeah.
Russian jump, and then you.
I got you. Yeah, like that's the bottom half of his body, and it's like falling to the side, and then that's.
Oh, see, I saw it completely flipped upside down. Like the top of the T are his legs.
Oh, okay. I got you. Yeah, I can see that. All right. So this is what I want you to remember. So this is that entropy always increases in practical situations. So the universe is spiraling towards chaos, and we're all doomed. But that's basically what I'm getting at.
I mean, we know that already.
Yeah. So at this point, I think we are done with thermodynamic discussion. We have a couple other things we can do. I didn't know if you wanted to make any adjustments to your stock, because I know that I recently passed you in the...
Yeah. Okay.
Okay. So
make
we're
the
going
adjustments
to...
that will make me win.
We're going to go look at that. So